Hi, I'm going to give a little talk about multiplying polynomials and other things, in fact. So I want to tell you what the idea of multiplication is. In my mind and in the minds of many, many mathematicians, the idea of multiplication is very simple in the sense that if we multiply two things together, for example, let's take and multiply the number 2, which is those are the things we're supposed to be most familiar with, are numbers. So if I multiply 2 times, say, 3, okay? Now the way we think of this in our minds, and everyone, not everyone, but many people know that this is 6. But I want to show you what these numbers correspond to. And I've drawn this rectangle here because when you think of multiplication, I think it's very healthy to think of finding the area of an object. It turns out that you can basically think that way for the rest of your life, and everything will be fine. I still think of it this way myself when I'm decomposing representations. So, okay, if we have this here, what I always think of is this: is I have something that's has length 2. So this line that I just drew these dots, that is if that has length 2, and if the width down here of this rectangle, important that it's a rectangle, you think of a rectangle, if that has length 3, then the area of the region inside, right, that is area 6. So you want to think this is a very healthy way of thinking about multiplication, is that whenever you're multiplying two things together, you're finding the area of something. That's how you want to think. So the area of that thing you're looking at right there, that area of that would be 6. Okay? So if this is 3 feet long, and this is 2 feet long, the area would be 6 feet, and then you have to multiply the feet times the feet, and that's why we get feet squared. Okay, so there's an idea of multiplication. It's a way of taking two lengths and finding an area. Okay. Now, let me draw this picture. And this picture will help you to be able to multiply polynomials with great ease. What I would like you to think of right now is the following. Let us suppose that we have the following. I'm drawing these two lines, and I'm going to draw an arrow. Whenever I draw an arrow, or when people draw arrows like this, if you've had drafting classes or not, or if you're into drafting or whatever you're into, whenever you see an object like this with a line there and a thing like that, what they're saying is that that's denoting the length of a line. So that's really a positive number. So I'm going to do this, okay? And watch this. So I'm going to write down some lengths, okay? And I'm going to write down a little abstractly. I'm going to introduce variables because, after all, having unknown quantities is the first step in creating useful mathematics. So I'm going to call this x. So when I write that x there, I really mean the length of this line from here to here has length x. Now I'm going to put a number here just for simplicity and for familiarity. When I put a 2 there, I mean the length of the line from here to here is 2, and that's what that means. And you must know what that means to understand the idea of multiplying that I'm about to present to you. Now, the length of that line then must be x plus 2, because after all, that's the definition of addition. When we add, we are concatenating. We're putting things together and combining them. So that must have length x plus 2. I'm going to do the similar thing on the side here. I'm going to introduce even another variable. Let's suppose that this has length. Well, let's make this just a number. Now let's go. Okay, let's make this length 3. And I'm going to say, actually, let me change that. I'm going to turn this into, because I want it to look very familiar to you in the future. I'm going to make this have length, well, let's say it's length x. I'm going to make this like 2x, just to make it 2x. There, now it looks right. That has length x. And now let's make this have length, let's say this has length, let's make it 1. Okay? Then we know that when we add those two together, we get the length of this line right here. So this has length x plus 1. Now, so what I'm going to do is I'm going to show you a way of finding the following. I'm going to show you a way of finding what we get when we have x plus 1, which is the length of the side of that rectangle. And if I multiply that by 2 times x plus 2, which is the length of the top of this rectangle. Now the key is to realize the following, that this diagram must be consistent with what we do in general principles when we're talking about finding areas of objects. So I'm putting different colors in here. So I want you to focus on the different regions that we're talking about, okay? So what I'm going to do is I'm going to write down the areas of the regions that I've colored there. Now, using basic principles that we've just talked about above, to find the area of this region here, I would have to multiply this 2x times this x. And we should know, after studying how to multiply monomials together, that this is 2 times x squared. Okay? So that is the area of that red region. Moving over to the right here, if I take, see the length of this line here that I'm drawing on now, that is length 2. The length of this line here, that has length x because it's labeled over here. Okay? So that makes this region have area 2 times x. Similarly, the green stuff has area just 2x, or 1 times 2x. And the area of this last box has area 2, or 2 times 1. Now, if we want to know the area of this entire rectangle, it is consistent with the way we define area that this must be the sum of the areas. So this is equal to 2x squared plus, now notice the way that this is set up, I can take this 2x and this 2x, and I can add those together, and I'm just going to write 4x. Son of a gun. Let me try that again. I'm just going to write, oops, get the line out of there, 4x, try that again. That's in erasing mode. Here we go. 4x plus 2. And that's all there is to multiplying anything. So let me do some examples now to show you how this one idea applies to all of these different things that we're multiplying together. They're all the same. And that's the goal of understanding mathematics, is to see that things are the same. They're not different. They're all just special cases of some very, very general rules. So for example, I'll draw this box here. And I like to use this box because it's a nice visual aid. It's really just a way of keeping track of what's happening here. So what I'm going to do is I'm going to find w minus 5. So I'll put w and a minus 5 here. Now I know that negative 5 is not the length of this number, length of this line. But if we use our imagination, we can see that we can think of this line that across there as being represented by this mathematical object that we're calling minus 5. So watch this. I'll put a w here and then a 5 here. And then what I'll do is I'll just fill in the boxes. So w times w is w squared. W times minus 5 is minus 5 times w. W times 5 is 5w. Minus 5 times 5 is minus 25. And just like before, what we see is that then the product of these two, so the conclusion is that if I take w minus 5, and if I multiply that by w plus 5, it's equal to what I get when I add up what's on the inside of the boxes. In other words, it's w squared. And now look, if I add minus 5w, and if I add that to 5w, I get 0. And then I just have to tack on a minus 25. Okay, so there's the example of what's called, those are called conjugate binomials. The word conjugate is very important in mathematics, and these are examples of what are called conjugate binomials. It's important when we study complex analysis, for example. Now let me do the exact same calculation, except using this box. Okay, so let me draw a nice box. I'll get my box drawing thing out here. I'll do this next example, which is called multiplying binomials with leading coefficient 1. Okay, so what I'm trying to do now is I would like to find out what x plus 4 is times x minus 5. So I'm just going to make one of my little boxes here. So here's my box. Just as a, like I said, a visual aid. It doesn't have to be a scale, just as a way of keeping track of what's happening, you see. We have an x, and this has length 4, and then imagine this has length x here, and this has length minus 5. So x times x is x squared. 4 times x is 4x. Minus 5 times x is minus 5x. And minus 5 times 4 is minus 20. So, by my principle, we see that this product here is equal to what I get when I add up all the things in the boxes. So it's x squared. And then if I have a minus 5x plus 4x, that's just minus x. And then I have my minus 20. So there again we see the utility of thinking about it exactly the same way. Some of you that have seen this in the past multiple times may think of this as an example or a sort of a geometric realization of the FOIL technique, something I typically don't like to mention the word FOIL, but here it is. I'll show you where they come in. What's in this box is the F, right? No need to call it the first. What is in this? Let's see. What's this? Where's the O? Oh, that must be over here, right? Oh no, here's the outer ones, for those of you that are into that. Here's the inner ones, or the corresponds to the I, right? And over here we have the last, right? So there, it's exactly the same. It's just the problem with the FOIL gimmick is it doesn't generalize, and that is a problem. Anything in mathematics that cannot be generalized is virtually useless. Okay, so let's take a look at this next one here and see how that goes. So I want to find out what this is called, multiplying binomials with two variables. Okay, so I want you to see that this is exactly the same also. 2x plus 3z, we want to multiply that times 7x minus 6z. So I'm going to do the exact same thing. In fact, let me just do it right above here. I'll erase this template here, and we'll just see that it all works the same. We just have to keep track of the fact that the top and the side of the box are representing the labeled objects. You know, those are the things that we're multiplying together, and then what will appear on the inside will be those things that we need to add together so that we get the product. So here we go. I probably should have just let me just draw another box here. All right, let's draw another box. It turns out it's easier. Okay, so here we go. Here comes our box. Okay, so here comes our box. Okay. Boink, boink, boink. Right. And it's going to have 4 things that I'll have to multiply 4 things here. So I'm going to put right here. I'll put 2x and 3z for the lengths of these two lines. This line from here to here, and this line from here to here. Then here I'm going to put a 7x, and I'm going to put a minus 6z here. Okay. So if I multiply, here I'll just do it this way. If I multiply this guy here, right, times this guy here, just so you make sure you understand this completely, because if you understand this completely, it's trivial. What you're going to get is the area of that spot right there. Now, so what do we get when we do that? Well, let's see. That's just going to be, let's see, 2x times 7x, that is equal to 14x squared. Okay? Now, if I multiply this 7, here, I'll change the color up a little bit now. So if I multiply this 7x, it'll be green now. This 7, oops, might be green. Okay. If I multiply this 7x times this 3x z, that will give me the area of this region here. That's the way that we view the translation of lengths. This may remind some of you of those problems where you had to find the missing length, right? You see, if the length of this is 7x, that's also the length of this, because we're drawing a regular rectangle. Okay, so then I'm going to write in here the length of that is 21xz. In a similar manner, down here we see we get minus 12xz, and here we get a minus 18 z squared. So, to make a long story short, if this is our symbol a is equal to this thing, a is also equal to what I get when I add these up, or it's 14x squared. And now notice we have 21xz minus 12xz. I believe that is, yeah, that's just going to be a plus 9xz. And then it's a minus 18z squared. Okay. All right, so I want to do one more problem to show you, basically prove to you that this technique is what we call, is generalizable and therefore valuable as a mathematical tool. I'm going to multiply this out, bypass this one. I don't want to do this one right here, but it can be done in the exact same way. So we're going to try to calculate this. We're going to take 6y minus 7x minus 6, and we're going to multiply that by 3y plus 2x plus 2. Okay. So now the only thing that's different this time around is that I'm going to draw a bigger rectangle, because there's the sides are made up of not 2 objects but actually 3. So you'll see what I mean, and this should be very clear to you how this occurs, and it should be very clear to you how this procedure can be generalized to all objects you would ever find yourself multiplying together. Okay, let me get the eraser out here and clean this up a little bit. So notice there are 9 boxes there, and those 9 boxes we are going to represent the areas that we will have to add together when we multiply the polynomials that we're looking at. So I'm going to think of this as having length 6y. This is having, well, I know it's not a length, but I'm going to say length improperly, minus 7y. This line corresponds to minus 6, 3y, 2x, and 2. Okay, so now we use the exact same principle that we have been using since nothing's changed. I'll write down what the area of this object is. This is 18. Maybe we should call it the generalized area for those of us that don't want to use the word area when looking at quantities that may not be positive real numbers. But this is a negative 21 xy. This is a minus 18 y. This box is 12 xy. This box is minus 14. It should look like a multiplication table, actually, because what I'm doing is I'm putting the products, you see what I'm doing? I'm putting the products in the spots that would be occupied if we multiply, for example, if I multiply this, not a 16, I'm sorry. So if I multiply this 6y times 2, I get the following. I get 12y. If I multiply minus 7x times 2, I get minus 14x. If I multiply negative 6 times 2, I get a negative 12. Now here's something that's really nice to look at. I'm going to circle objects. This is another really beautiful thing about this, is that I'm going to circle objects that are what we call like terms, and you should see some nice symmetries here. So for example, this thing here, this can be, and I will in the future, in about 2 seconds here, add this to this thing right here, okay? Notice that this red thing here can be added to this thing here. And this can be added to this. So there's a very nice symmetry that you can realize, and it makes things very easy to write down. So let me show you what I mean. So without really thinking much about this object, which I'm also calling A, I can now rewrite in it, after I multiply it, in the following form. So here, so A is equal to, and I'll put it back in terms of black, and I'll show you another thing I like to do just to keep track of things. You got to watch this in real time, because I'm going to write down it's equal to 18y squared. So this guy, I'm going to circle it. That means I've taken care of it. Done. It's just like an accounting thing, right? Now if I take a minus 21 xy and I add 12 xy, that's a negative, I think it's what? Is it 9? Yeah, somebody should probably check that. Minus 9, right? xy. So that's taking care of this guy here and this guy here. Now I'm going to move on to the next one. So I'm going to write down a minus 6y. Took care of this one and this one. Now I'm going to write down minus 14x squared. That took care of this. I'm going to write down minus, now let's see, 18 plus 14, that's what is that, 32? Okay. 32x. Took care of this, and I'm going to subtract 12. So there we have it. Okay, so I hope this makes sense, and if it doesn't, you should really work hard so that it does make sense, because it's a really wonderful way of thinking about multiplying polynomials together. And so I hope you enjoy it. If you have any questions, please ask your instructors. And it's sort of a generalized, more geometric way of thinking about FOIL. So thank you very much. Bye.